Okay, so let's take a look at 5.4 here. So 5.4 says evaluating trigonometric ratios for any angle between 0 and 360. So far you've been doing trig ratios for angles that are acute, which means angles that are between 0 and 90. We're going to look at all the way around a circle between 0 and 360. So it says trigonometric ratios have been defined in terms of sides and acute angles in right triangles. They can also be defined for angles in standard position of a coordinate grid. Angles can be measured from 0 degrees on a coordinate grid in a counterclockwise direction. Let xy be a point on the terminal arm of an angle theta in standard position. The side opposite theta is y and the side adjacent to theta is x. The hypotenuse r can be found by using the Pythagorean Theorem. So here are your two drawings that is in coordinates, in number 1 quadrant, and this is in quadrant number 2. And in order to use the hypotenuse, you can find the hypotenuse using this formula here. So let me just go over this with a little better explanation. So let's say you have a Cartesian plane here, and you are talking about this terminal arm. Remember, it's talking about a terminal arm in standard position. A terminal arm, doesn't matter how long the terminal arm is, in standard positions starts here at 0 degrees. And the terminal arm can rotate clockwise. Okay, so it rotates around and around and around. So this terminal arm just keeps rotating around and around and around the circle. Obviously, if it rotates to here, this is 90 degrees. If it rotates to here, this is 180 degrees. If it rotates to here, this is 270 degrees. And if it comes back to the start, it's 360 degrees. So this is coordinate number 1, or sorry, quadrant number 1, quadrant number 2, 3, and 4 right here. And again, this terminal arm rotates in a counterclockwise direction. So let's talk about if you had the terminal arm rotate into quadrant number 1, what would happen, what this would look like. So if we have, again, this rotates round and around in a circle, and if it rotates into quadrant number 1, for instance, right there, if it rotates by this much, and we'll call this theta, if it rotates into quadrant number 1, it's very important you understand that this quadrant has all angles between 0 and 90 degrees. So all of your angles are between 0 and 90 degrees here, so these are acute angles here, which is what we've been dealing with. And if I draw a line from this point here is going to be xy, and of course your x will be a positive x, and your y, your height, will be a positive height. And if we draw an imaginary line straight down to the x-axis, we'll always go straight down to the x-axis since we started at 0 degrees here. This is 90 degrees. Now the distance, if we look at this triangle from here to here, is your x-coordinate. The height of this triangle is your y-coordinate. And then the distance from here to here, we're going to call this r. So why would we call that r? Well, if you notice, this rotates around in a circle, and the distance from the middle to the outside edge of a circle is called your radius. And so looking at this, we can relate all three side lengths using the formula, the Pythagorean Theorem, which is c squared is equal to a squared plus b squared. But in terms of these letters here in this picture, the hypotenuse is r, so r squared is equal to side 1, which is x squared, plus side 2, which is y squared. And so this is the formula for figuring out your radius, otherwise known as just the formula for a circle that you learned in grade 10. The other things you should know is if we take a look at sine theta, we take a look at cos theta, and we also take a look at tan theta in quadrant number 1, we know that sine is opposite over hypotenuse, but according to this diagram, instead of calling these things opposite, hypotenuse, and adjacent, we're going to call these things x, y, and r. So in relationship to the theta, your y value is your opposite, your x value is your adjacent, and your r value is your hypotenuse. So sine theta is opposite over hypotenuse, opposite is y, all over hypotenuse is r. And notice both of those things are positive numbers. So sine is positive in quadrant number 1. Your cos, being adjacent over hypotenuse, according to this diagram, adjacent is x, all over hypotenuse is r. And so cos theta is x over r. And x is a positive number, so is r. So positive divided by a positive, that makes cos positive in this quadrant as well. Last one, tan. Tan, you know, is opposite over adjacent. And we know that the opposite is y, over adjacent is x. So tan theta is y over x. And y is a positive number, so is x. So positive divided by a positive will make tan also positive in quadrant number 1. So since sine, cos, and tan are all positive in quadrant number 1, I'm going to label quadrant 1 with a big A for all are positive. If we take a look at the second quadrant, quadrant number 2, and see what's going on in quadrant number 2, again, if I start off with a terminal arm in standard position, which is 0 degrees, and we know that this terminal arm rotates counterclockwise in a circular fashion. If it rotated into quadrant number 2, which is over here, this is what the picture would look like. It rotates into quadrant number 2. So this is how much it opened up by theta. So that's your theta. And we know that in order to be in quadrant number 2, if this is 90 and this is 180 degrees, we know that theta is in between 90 and 180, or all of your obtuse angles. And then if we go to label this triangle here, this point right here, P, well, if I draw a line straight down to the x-axis again, where this is a 90-degree triangle, the distance from here to here, that distance will be a negative number, or in terms of your Cartesian plane, this will be a negative x. This will be a positive height, y. R, your radius, is always positive because that's just measurement. So my point is going to be some negative x and some positive y, this point P. And then, if we take a look at sine, cos, and tan in relationship to quadrant number 2, if I take a look at sine theta, cos theta, and tan theta, remember, I know that sine is opposite over hypotenuse, or y over r. So opposite is your y, adjacent is your x again, and hypotenuse is your r. So sine is opposite over hypotenuse, which is y over r. And we know y is positive, so is r, so this is positive. Your cos is adjacent over hypotenuse, and adjacent in this case is a negative x all over hypotenuse, which is r. So we know cos in quadrant 2 is negative x over r. Now a negative divided by a positive will make cos negative in quadrant 2. And then if I look at tan, tan I know is opposite over adjacent. Opposite in this case is y over adjacent is negative x. So I end up with tan is equal to y divided by negative x, and that will make this negative. So in quadrant number 2, the only thing that is positive in quadrant number 2 is your sine function, or your sine. Sine theta is positive in quadrant 2. So I'm going to label quadrant number 2 with a capital S for sine. Okay, so in quadrant number 1, all of them were positive. In quadrant number 2, only sine is positive. And if I take a look at quadrant 3, I can do the exact same thing for a terminal arm in standard position, and it rotates in a circle. If it rotated into quadrant number 3, which is over here, if it rotated into quadrant number 3, that means this is how much it opened up by, and so that's your theta. And we know that to be in quadrant number 3, theta has to be an angle bigger than 180 degrees but less than 270. Okay, this is not obtuse or acute, it's just angles between 180 and 270. And so, if I take a look at sine, cos, and tan over here, I'm going to label this point P and draw a line straight up to the x-axis again, where this is 90. The distance from here to here, the horizontal distance, this is going to be a negative coordinate for x, and going down by this much is going to be a negative coordinate for y, and your r is always positive. It's a measurement. So looking at sine, cos, and tan for quadrant number 3 and labeling this, we know that opposite is your y, adjacent is your x value, and r is your hypotenuse. So this point here is going to be a negative x and a negative y. So sine we know is opposite over hypotenuse. Opposite is negative y over hypotenuse is r, which will make sine negative. Cos is adjacent over hypotenuse, which is negative x all over hypotenuse, which is r, which will make cos negative. And tan is opposite over adjacent. Opposite is negative, and so is adjacent. So that means that tan, a negative divided by a negative, ends up being a positive. So the only thing positive in quadrant number 3 is 10. So I'm going to label that with a capital T for 10. I'm going to let you do quadrant number 4 on your own, but just so you understand the rule here, this is the cast rule. We had A for all here, S for sine, T for 10. This is going to be cos if you do this one properly. So this is the cast rule, okay? And so the cast rule just indicates that in quadrant number 4,